Hi, and welcome to this short Taiwan Semiconductor webinar about our MOSFETs and more in particular about our automotive MOSFETs. We have launched our first automotive MOSFET split gate technology using split gate technology in March this year. Here, we're in the process actually of releasing quite a few of them here and also increasing our presence in the automotive market here. What you'll see today is a screenshot of where we are. We're of course moving ahead daily and contact your regular sales contact here to get the latest updates on what is released and not released here. But what we wanted to do is just give you a snapshot of where we are because we are happy that we introduced our first automotive split gate MOSFETs. In this brief webinar, we'll update you about our 40 and 60 volt product portfolio, our automotive releases here, our supply chain, technology and product positioning, and also support tools. And we're talking today about PerFET, our split gate technology here that we've launched, and PerFET is our trade name for this to describe the split gate technology. So we're in the MOSFET business for over 10 years, and this is not our first automotive MOSFET. Our first automotive MOSFET was released in Q2 2020 using standard trench processes here. We've been working on split gate technology, or we sometimes also used in the business as shielded gate technology for several years, and we produced our first product for the industrial market in Q2 2022 here. Now we have introduced our first automotive AEC-Q101 qualified product here in split gate technology or shielded gate technology here. And we may have capacity here actually for split gate technology MOSFETs automotive ones in 2023. So we are actually effectively looking for business here. As you know, we are known as a rectifier company here, where we have 95% of the product portfolio here to do your design in. MOSFETs are a little bit different. We have 280 part names, of which 194 are active. We're probably over by 200 here. This was counted about a month ago here. So what we're trying to do with this webinar also help you in distribution or our sales channel focus on what is available, what is our strength, and where we are active, so you don't randomly run after business and then find out that from all the 10 parts we have, only one you're offering or cross-referencing, only one is available. So we'd like to focus you a little bit more on our capabilities in MOSFETs. As I told you, the first trench MOSFETs were automotive MOSFETs were released in 2020 here, and what you see is that these products are all 40 and 60 volts here. You can read yourself here the gate source voltage here, the breakdown volt, the RDSON here for the 40 volt and the 60 volt version, and also for the dual versions 40 volts and 60 volts here. What you'll see is that we've only introduced standard level MOSFETs here in this using this technology here. They're already at 175 degrees C, and their small die, or their big die actually, because of the standard trench process, may have some advantages in the future here. So don't discount them. We're selling them, and you know, these are still available here in the market. But obviously, for new designs, the new technology is probably it will be the more preferred one here. So why is that? Of course, split gate technology or shielded gate technology has a number of advantages over the trench designs. I'm not going to go in the details here, but the split gate here, you know, refers to these parts here, where this part is actually connected to the source here. So what it does is it does two things. It reduces the specific on resistance here, so that is for the same die size and things like that, you get a better RDSON. So that's one advantage here. There could be over 50% reduction compared with previous generation, depending also if you include the copper clips in this case here. So you can also achieve RDSONs in smaller packages here. When you look at the other area of improvements is the switching performance here, where you have a 40% improvement of the figure of merit, which is usually the QG multiplied by the RDSON here. This is best symbolized here by the graph here on the right hand side. Here you see the Miller plateau, or where the QGD is active here, and in this area both you know, the MOSFET conducts current and voltage here, has voltage over it. So this is the area here where you have most losses here. So if this is smaller here by a significant reduction here, the MOSFET switching losses will also be improved here. There is a reduced input capacitance, output capacitance. The EMC behavior comes from the internal snubber here, is also helps here. And of course, this technology is ideal when you go up to high switching frequency applications here. What we've also done here, and that is linked here to the split gate technology here. The split gate technology is designated with the use the NH in the part name. The other one is S and B in the part name here. And what you'll see here is that the temperature coefficient of the RDSON is lower. That is, of course, beneficial, and that is especially important for people in automotive applications, where you find that the MOSFET works in higher temperature here. This, of course, will give you significant benefits here. Of course, the process is ASIQ qualified here. So these are all the advantages linked to the performance here. What you see is here that these are the products that we have in production here for the industrial part names. The industrial part names you can understand, see by using the word TSM S in the part name here. So we're going for 1.9 to 7 milliohm here and 40 volts here in standard level here, and VGS 16 and 20 volts in standard level and logic level here. And of course, the different threshold voltages, the lower threshold voltages here for the logic level parts here. So this is what obviously what you can see here. We also have a dual version already available here, and we have the PDFN 3x3 versions also available here in 5.6 and 7 milliohm versions here. These parts are all the PDFN 5x6 parts are all manufactured using aluminum ribbon bonding. So this is called aluminum ribbon bonding, where the bond wires are attached to the die like this here. There is also something called copper clip, which has an inherent slightly lower RDSON here. So this is, for example, these two are the same die here. They have an advantage of 1.9 to 1.3, and that's the difference between the aluminum ribbon bonding and the copper clip. There's a trade-off here. Of course, this helps you with a better RDSON here, but it's also slightly more more expensive process here, to put it straightforward here. So those are the trade-offs we have to make for each die size. So what you see, this is already in production. We're shipping these products also already in significant volumes here. So what the exciting part of the presentation is that we introduced in March already, a number of MOSFETs here, 40 volt MOSFETs here. And as you can see, in April and May, we're completing the whole series here. So the next couple of months here, we're going to have 1.9 to 7.6 volt milliohm MOSFETs, 40 volt, also in the PDFN 5x6 package here, available for automotive customers here, which is very exciting for us here. So this is a major milestone for the company here. We should notice here that, of course, we also want to do this in copper clip and in PDFN 3x3 packages, but this will take a little bit longer to qualify for automotive production here. So we're thinking more beginning of next year, 2024, for these products to become available also for automotive customers. The last slide we don't want to give you too many slides with part names and that type of stuff, but this one is coming soon. So this is, we're a couple of months away from being able to promote and ship the 60 volt MOSFETs here. So this is something we're also exciting about here. So we're going from here from 60 volt here. Initially, we're going to go from 2.6 to 13 milliohm RDSON packages here with a 60 volt breakdown voltage, things like that. So those are coming soon. Here again, the same thing with the logic level and standard level MOSFETs here. Here the gate voltage is always 20 volts, as you would expect from a 60 volt MOSFET here. Again, for the automotive versions, these are the TSM, so these are the standard versions here. The automotive versions will be named TQM, and it's the same thing as with the 40 volts. The copper clip and the PDFN packages will be later. They will come only next year. So this is what we actually wanted to present to you of our new products and our exciting new milestones in Taiwan Semiconductor. We've launched this product, and all of these products are launched with a complete package here. You can see here a SPICE model here, Snap EDA for layout functionalities, and of course data sheets here. We also have an applications team that is working hard on making comparisons with competitors and things like that, and helping you solve all our problems here. Also a few other support tools we're having are the following here. We have the application note 1011, the PerFET MOSFET advantages here that compare split gate technology with trench MOSFETs here, more or less similar to the earlier slides we have shown here. Then we have another application note 1009 about wettable flank packages here. I think everybody in automotive actually knows why wettable flank packages are used, and they are mandatory for this business. But as you can tell, with the split gate technology, we only have one package, so we also use wettable flank products for non-automotive applications, industrial. And in that business, not everybody knows why these wettable flanks exist here. So if you come across a customer that doesn't know this, this is a good application note to show them and to help them explain why we have wettable flank packages here and why we're doing this on our new TDFN packages here. What we have here, and also this is of course a snapshot and a work in progress. Ask your sales force for the latest cross-reference list here. I've copied and pasted one for automotive MOSFETs. We also have one for TSMs, non-automotive MOSFETs here. So these lists are continuously updated here. You already see here our main competitors here. They may vary in region. I'm making this recording in Europe, so of course we're seeing a lot of Nexperia, Infineon, and onsemi. I'm sure everybody also sees Vishay and ST, but some regions may see also other suppliers active in their market here. Going on here to MOSFET cycle time, or our supply chain, and why we think this is an exciting entry into the market here. Sometimes you listen and hear that people say, the lead time or the cycle time, which is the perfect light manufacturing time if there are no bottlenecks anywhere here. The cycle time, usually people say, it's about 1 week per mask or something like that. And you can see we have a 6-mask process here, or at least that is what the script is here. However, the trench photo mask is actually quite complex and takes a little bit more time. So you'll look at the mask of front-end cycle time of around 9 weeks here. Then comes what we call the chip probing here, because the die are big, so we want to test them before assembling them here. And then we have BGBM here, back grinding, back metallization. That stands for the MOSFET RDSON is determined by the thickness of the MOSFET here. So you want to slice the MOSFET and make it a little bit thinner here to improve its RDSON here. Once you go to these MOSFETs of 3, 4 milliohm, that type of stuff, this extra manufacturing cost is easily offset by the reduced RDSON here. So this adds a chip probe and BGBM, the back grinding, adds each to about 2 weeks to the perfect cycle time here. And then you have the assembly here, 3 weeks around here, in that area here. Now here is where the critical thing is, where we distinguish ourselves, or maybe from other suppliers here. Our partner on the front end is UNC here. They are for the split gate technology MOSFETs here. They are not only our foundry partner, but they are also investors and sit on the board of directors here. So they are very important partners, let's put it like that here. They of course have huge wafer fabs, and as lithography moves for ICs to finer lithography or to more complex ICs, we expect that more capacity becomes available in the area of 0.18, 0.16 micron, which is typically the processes used on MOSFET technology here. So this actually here, we have confident about our front-end supply, and that is not our limiting factor, and that is the limiting factor, has been the limiting factor for a lot of people over the last couple of years here. For us, of course, it's the back end that is the critical factor and also our critical investment here. So we use one subcon, but we also have our internal factory called I-LAN in Taiwan here that is potentially being expanded and also used now as a MOSFET backend factory here. So we are investing here, and this is also to demonstrate our seriousness and our commitment to the MOSFET market here. that we're in this business for the long term here, that we're expanding our back-end capacity here. In this case, the investment is at the moment for PDFN 5x6 packages, our first mass volume packages for automotive MOSFETs. So on the back end here, you'll see that we only have the wettable flank package here. These are solder pad layouts, suggested solder pad layouts, so you can be compatible with all the other competitors here. May that be an Xperia or Onsemi or Infineon on the first line, or ST and Vishay. So you can make all those packages fit on a single footprint here, and so we are comfortable also on that case here that we can be competitive or compatible on the back end package here. The big question is, of course, is when you start cross-referencing and that type of stuff here. So product positioning here is where we put our split gate technology is actually going to be linked to the process. We have developed a process, and that has a certain figure of merit here, which you can't change. For the figure of merit is the RDSON multiplied by the QG or QGD. So if you choose a certain RDSON, you also get the QG or QGD automatically, and you get the AC parameters automatically. So the process determines how you compete with other people. The specific RDSON, which we mentioned before, is the RDSON per square millimeter. And all these things are linked to a voltage of the process here, 40 volts. So there is no point in going, if you have a 40 volt design, crossing it with a 60 volt MOSFET here, because frankly speaking here, those figure of merit and the RDSON per square millimeter are much worse here. And the figure of merit is what most people will look at initially, even though it's a crude benchmark here. It's something easy to see on the data sheet, but very few applications are balanced where 50% of the losses are RDSON and 50% of the losses are switching losses. Most of the time, one of the two dominates here. So that's something you need to keep in mind here. When you go for cross-referencing here, it's a question here. You first want to match, as I mentioned here before, the breakdown voltage, then the package here, and then the RDSON here. That gives you automatically all the other parameters here. Of course, you want to cross logic level with logic level and standard level with standard level. That's the best thing to do here. What I say here is that good cross-referencing here depends on the application knowledge here. So some parameters are more important in some applications than others here. So that it does help to understand the application here if you're working in distribution or one of our sales channels, to get across here or to get a good feeling if our MOSFET will work in the application or how well it will work in the application. So those are just hints and tips for you to keep in mind here. If you look at it here, things like that, it's the general MOSFET applications are here in three parts here. And actually, we're going to look a little bit on the right-hand side, the switching power supply later on here. But, in automotive parts, you're going to be more in the middle here, which means the application is the motor control here, 3-phase or 2-phase and that type of stuff. In that applications, the RDSON losses are by far the dominating ones, and the AC losses are low here, 10-20% or even less or something like that here. So the specific RDSON is the key parameter, and matching the RDSON here should actually do the job here if you're cross-referencing here. So that is a good first approach here, which will work here. The same actually on the left here, on-off switches here, or in case of automotive electronics, polarity protection here, but you also have them in a lot of applications, non-automotive applications here, what they call load switches here. Here actually the MOSFET is turned on once in the application here, so it's actually all RDSON losses here. So if you match the RDSON, you're safe and you're doing a good job crossing the Taiwan Semiconductor device in the application here. The one on the right-hand side is switching power supplies here, where the figure of merit here is the more important parameter, because the switching losses can no longer be ignored here. And in some areas here, especially when you have low loads, like a 10% load or something like that, you'll see that the switching losses could be even dominant here. So the figure of merit becomes important here. This is more switching power supplies. It's going to be the case also, figure of merit is going to be important in DC converters for automotive. And this is, you know, something you need to keep in mind for the future here. 40 volt MOSFETs are not going to use that much in DC-DC converters. You're going to have to go to higher voltage MOSFETs to be, you know, be using them here. But you might come across it in an ADAS application or something like that here. So it's not exclusively switching power supply here. A small portion of the power of the automotive MOSFETs will be used in this area in the future. So here a little bit more about the application here, and we're talking here about 40 volts here. On the left hand side, there's just one thing I just wanted to mention here, because in Europe, in your day-to-day life, you're probably not going to cross these load switches in automotive, but you're going to cross them for load switches in simple power supplies and that type of stuff. And we have a lot of existing SOL23 non-automotive products here and that type of stuff. So you could check and do the full cross-reference here, but this is an area where we don't have the full capability, or this is where, you know, where you will notice that our number of part names is limited to 200 or something like that in SOL23 here. So we have a more limited product portfolio here available here. So in this case, I would still cross it and try my luck here. You match the RDSON. It could be that the threshold voltage and the gate source voltage and a few other things are a little bit different here. Also the AC parameters here, making it difficult to drive from a microprocessor, but it could work or it could not work. I can give you 3 reasons why it could work, and I could give you 3 reasons why it couldn't work. I would still try my luck in this case for these load switches here in SOL23. For the middle one, the inverter, I think we've said it all here, right? So just the only thing is, you know, cross logic level with logic level here. And of course, in automotive, the temperature coefficient of the RDSON is also important here. So you want to use, in that case, the new series also for as an advantage here for a better temperature coefficient here. For the high switching power supplies, there's a lot of AC parameters, the gate resistance and that type of stuff. It's all important, and it's all things, you know, that do influence the performance quite a bit here. But to be fair to you, or to be honest to you, once you've chosen the RDSON, you just get these parameters here. The only thing you need to remember here, that it's a little bit counterintuitive sometimes. If your switching losses are higher than your conduction losses here, then it makes sense to go to the smaller die, not to a bigger die. So sometimes that is done counterintuitively here. Our applications lab can help you here. Sometimes you can fit our MOSFETs in by adjusting the RG or other things in the drive circuit here. So if you are stuck here, contact us and we will be able to help you, or we will try to help you cross-reference and match the performance of the MOSFET in the circuit with our applications lab and their capabilities. So we told you that in this case, we're going to have to, if we're comparing ourselves, we're going to have to compare ourselves with certain processes here, because that determines the capability of the MOSFET if you cross-reference here. The most famous process in the business, the market leader also in medium voltage MOSFETs, is Infineon, of course, and there's no doubt about it. And OPTIMOS 5 is probably the most famous process, their most famous process here. If you go here, and I'll let you go here, this is a complex data sheet. I didn't circle it here in this application here. Sometimes I circle the thing here. So this makes it a little bit more complex for you, but you'll have to look at this slide here for a second while I'm talking here to see if you can determine the figure of merit yourself here. And you know, you can actually see here, what you see here is that at 10 volts, you have 6.1 milliohm spec here, and you have a QGD of about 3 here. We had 10 volts have a 5.6 milliohm spec, but of course a QGD which is slightly higher, 3.5. The figure of merit are not that far away from each other. So what we can say here is that actually we can feel comfortable about crossing OPTIMOS 5 MOSFETs from Infineon here, especially in automotive applications here, where the switching losses are low here. So there are always minor differences. There is no such thing as two MOSFETs which are the same. There's always a difference between the two. You will never get the same graph or the same switching waveform and that type of stuff. It's impossible here, but we think we're going to be close enough and capable enough to compare with our OPTIMOS 5 friends here. And that's our target business here in automotive. One thing when you cross here, that's something here I will say here. It's our first product line which we launch here. This is the NH series here. And what you'll see here is that we have a fairly big gap between the typical and the maximum here. So our max here is 4.3 milliohm and 2.9 here. Yeah, I took an Infineon part here with 1.9 here and 1.5. So they are actually tighter. So their specs are a little bit tighter here. And we also have a 1.9 here, 1.9 here, we have 1.3 here. So this is our first spec here. So in our case, what you should do actually here is see if you can cross the typical voltage, the RDSON, not the max here, if the customer will agree to that here. So that's a small hint we would like to give to you with the crossing the MOSFETs here. The figure of merit sometimes is distorted by using copper clip or versus aluminum ribbon bonding. So that is something you need to keep in mind here. So our technology is pretty good here, but the figure of merit sometimes will be better if you use a copper clip here, which we will introduce also on the larger die of the MOSFETs. Last slide here. So benchmarking is good, or the first thing here, the crude method here is just look at the data sheets, and that's the first way people just look at it. You can't avoid that. Is it realistic or not? That's another question for the application, where the switching or the conduction losses may be different here. But what you do see here, for example, we put this in a synchronous rectifier power supply here. What we have here, we made a 480 watt power supply here, 40 amp outputs here, so that's a 12 volt output voltage here, and we use 40 volts here. And so we're switching at 150 kilohertz here. And what we're seeing here is that also the efficiency is pretty similar here. The critical ones here, of course, if the RDSONs match here, then you would expect this at full load to be pretty similar here. If you go at light load, of course, here, 25% load or light load here, you'll see, of course, that the AC losses are becoming more and more important here. What we'll do see here, though, is that overall the performance of our part is good here. Would you say, of course, 150 kilohertz is typical for the power supply market here, but what we can deduct from this, if it does perform well at 150 kilohertz, you can probably be pretty sure that it's going to be okay at the typical automotive frequencies, which are less than 40 kilohertz, 32 kilohertz, or even less here. So that's what people use in their switching performance. So that's why we're okay saying that we're okay and fine against OPTIMOS 5 here. So we've got more work and done work done, so to prove that, or we can prove that we are competitive versus Trench 9 from the Xperia, Trench 6 or Trench 10 from Semi here, the newest versions. We also look fairly good for automotive here. So we're actually benchmarking and continue to benchmark. And if you have specific questions about one process of a competitor here, we can supply you more data here. It would go beyond the scope of this webinar here, but there is more benchmarking available that gives you a hint on how we will perform in circuits here with other major suppliers in the industry. Every MOSFET has a different competitive landscape here. So sometimes you'll see, depending on the die ratio here to the cost of the die ratio to the package ratio here, you'll see that we will perform differently in that type of stuff. What we do see here are some of our biggest successes in the beginning are for the smaller die, the 7 milliohm or the 7.6 milliohm double here versus, for example, a dual from ST here, or for example the 7 milliohm PDFN 5x6 single here. The reason for that is that packages like this here may be very complex and maybe over designed for copper clips and that type of experience here. So they might not be an experience or Infineon's favorite package here. So this is why we're actually also competing very well here on the lower end, specifically on the scale of the lower end of the or the smaller end of the die, the high end of the RDSON, I should say. It's high end of the RDSON here, at the higher end of the product range. So that is a overview of our product positioning for where we see our MOSFET market here. So as a summary here, we designed our first split gate technology MOSFET in process here, or shielded gate technology MOSFETs. We built up a reliable supply chain for MOSFETs here that is AEC-Q 101 qualified here. The technology we developed is competitive here. We introduced AEC-Q 101 qualified MOSFETs. This webinar, as you saw the roadmap or the introduced packages, of course, is just a snapshot. We will regularly introduce this with information, component engineering newsletters, etc. here. But you can expect a lot of activity from us in the next couple of months here. TSC is investing in MOSFETs heavily, so we want to make sure that we are known also as a MOSFET supplier, not just as a rectifier supplier, but MOSFETs are key to us here. There's a long-term roadmap here to expand our served available market. So we will expand with higher voltages, going to more voltage in the medium voltage range, and maybe also our packages here coming up next year. So we will continue to expand our range here. And yes, the MOSFET, the message is TSC is the MOSFET business for the long term. Not, all MOSFETs here, but targeted businesses here in the medium voltage range here, which will be interested for automotive MOSFET people and other people that, active in this business here. Thank you for your attention. And if you have any further questions, please do not hesitate to contact your local sales rep or person. Thank you.